This talk is about a paper that I just submitted to ICLR. It's about toward agents that reason computation. So I'm going to explain what I mean by the title. If I drew a graph and on the x-axis we had how much practice the agent has had on a task, like maybe it's playing the same level of the same game constantly over and over and over again. Some of you may already know that the energy that it uses is constant. It's constant when it's a novice, when it's first learning how to play the game, it's acting randomly, it's not doing very well. Sure. It's also the same when it's getting better. It uses the same amount of energy over time. And it's even the same when it's hit superhuman performance. It is a master at its game. Maybe there's nothing more to learn. That's not quite how people work. As they get better at a task, maybe they're new, maybe their cognitive load starts to increase. Or they start thinking harder, they use more of their cognitive resources to do better at the task. And as they get better, this guy's like holding his head because it hurts so much. Maybe there's like an inflection point. Like at some point, things start to get easier. There's no longer, you're not pushing that rock up the hill so much. And then as you're getting better and better, maybe you're finding more efficient ways to think about the problem and process your stream of experience. And over time, your energy consumption on this one task should drop over time. And then this guy at the bottom right is really happy because look at all that free energy look at all that energy it's now freed up. That person could use this energy for other tasks in the future, or it could use this energy to get even better at the task. Agents are not currently like this. They have a constant energy draw. It doesn't change as a function of their experience, and it doesn't change as they get better at the task. So right now we're working through the motivation, and now let's talk about these agent designs. On the left here, we have GT Sophie. GT Sophie was designed to be really good at autonomous racing. This is an agent that has the same characteristic that I'm trying to describe. It operates at the same rate, it uses energy at the same rate. Even for the Balloons project, the agent is operating at the same rate. It's like once every 3 minutes, that kind of thing. And DQN on the right here, it's playing video games, it's playing the same levels constantly over and over, and it's still using the same energy over time. Now we're going to focus on DQN, and we're going to focus on the problem that it was designed for. And we're just going to look at one of the games. The game is called Asterix. Asterix is down there at the bottom. He's running away from a musical instrument behind him, and he's trying to gather all these ancient objects. This is the opening game stage. This is the first frame that the agent is going to see in the game. And this is the player that the agent is going to control. At the bottom there are the lives. So it has 2 lives and it has a score. And these are the collectibles that it's going to pick up, and these are going to change over time. And when they change, it's going to get faster, the game's going to get harder over time. And then this is the lie that the agent is trying to avoid. And let's look at DQN playing this game. On the top is the gameplay, and on the bottom there is basically my proxy measure for energy draw. It's the rate of decision making, the rate of the agent observing the frame, computing what action it should do next, and then it skips a few beats and then does it again. I'll come back to that later, but it's a flat line, and I want you to pay attention to what's going on in the game. Like, as you can see, it's hiding in the corners, waiting for the next wave. It's probably strategically placing itself. But the compute is still at a constant rate, regardless of what's going on in the game. So yeah, there's downtime between waves, and the energy draw is the same. As objects get faster and faster, its energy draw is still the same. Even at the start of the game, when there's nothing visible for 60 frames, the agent is still using the same rate of energy. So yeah, laboring the point there. So let's look at how this agent was probably designed. Again, this is the opening frame, the 0th frame. And let's try to understand how the agent is processing its stream of information. So it's going to observe, it's going to get a pre-processed image. Maybe it looks like this. It's going to try to extract useful features about the world. Let's represent that with the square. And it's going to use these features of the world to select an action, and then it's going to send it to the environment. Immediately, the environment will go on to the next frame, and as you can see, nothing's happened. This game runs at 60 frames per second, and nothing much happens between consecutive frames. Of course, the designers could see this, and I'll illustrate that one of the optimizations here. If we repeat the same process, what the designers have done is they repeat the same action for some number of frames until it uses compute again, and then maybe picks a different action. So this is a way that designers have found, well, if we just let the agent replay the same action, well, then it can amortize this power draw over time. So what ends up happening is the energy consumption is lower. It's lower than if you acted on every single frame. So designers are already quite aware of, like, we have a lot of tricks. We have a lot of design choices that can make these systems more efficient, and quite a lot more efficient. This system is designed to act on like once every 4, once every 5 frames. So yeah, it's got this design choice got an optimization of 5x or 4x. And this is the agent that you guys were just looking at. It does have optimizations. Designers can anticipate some of the challenges this agent will face. And they can maybe foresee at design time ways for the agent to be more optimal about using its training resources. Cool. So maybe we want to learn a bit more about, like, how did designers come up with this? So if we drew a graph with performance on the y-axis, maybe 100% is like, this is good enough agent performance. And on the x-axis is the average compute cost. Maybe that's cheap and expensive. The top left is good. It's really cheap, it's really good. In the middle is fine. And in the bottom right, it's really bad. So how did the designers maybe figure out a fixed rate of using energy? Well, they probably just tried a whole bunch of things. They have this trial and error process of making the agent operate in a certain way, and then maybe this is like, if you act on every single frame, it's quite expensive, and then you train and you observe how does the agent perform and how does it kind of operate within the design constraints that these people have. Notably, these are design constraints that the agent can't see. We don't give this information to the agent. And maybe you try some more options. Maybe you're doing like a binary search, you're going to skip more often. And it's on the cheaper end, but it can't get enough performance because it doesn't have a lot of granular control over how it's moving these players in these games. And then at some point, the designer is going to find a sweet spot where the compute cost is good enough and its performance is satisfactory. They probably had some idea of what is the sweet spot. We want cheap enough for people to run more experiments and good enough to get the headline of we're beating humans in this task. So yeah, and of course designers have to think about a lot more things than just that. They have things like, what is the capacity of the machine that we're deploying this thing onto? These are all things that the agent doesn't see, but designers have to reason about this thing. And they find something that's probably just right. So connecting this back to the motivation of the talk, how agents use compute is fixed from design time. Designers find ways for agents to use compute efficiently by kind of following a trial and error process. This process kind of looks like you come up with the design and you train the agent. You observe its performance and you observe other metrics that designers care about. And then you make changes. You build an intuition of how this agent could be improved on in the future, and you make these changes, you observe their performance. And this kind of creates like a design cycle. And this is the result. On the left is a game called Pong. The agent is controlling the green paddle on the right. The scores are at the top there. And these are two very different games, but they're with the same agent design. And Pong is a notoriously easy game to master, except when it misses the goal. And on the bottom there, you can see the charts. They're using the same amount of compute. These are very different games, very different experiences, very different opportunities to use compute resources to the agent's advantage. And designers have to foresee these kinds of experiences at design time and get our agents kind of prepared for that. I'm going to move on. Cool. So I guess what I'm trying to illustrate here is that, you know, you might have a design of an agent that's good for one kind of game, and it might not be the same for a different kind of game. So even within an agent design made for the arcade games, there's still kind of a compromise across games as well as inside of a game. Like I was talking about the moments between waves where the agent could have like rested for a bit. I'm also talking about across games. Cool, so I'm going to talk about the method, like what was my approach to trying to address this? So coming back to my illustrations earlier, yes, the power draw changes over time, but like I'm saying, this is a fixed rate. It's fixed at design time. So yes, the designers can find ways to reduce the overall energy consumption or the overall average compute cost. Kind of the intuition for what I'm proposing is using the same techniques that designers use. Just let the agent have access to actions that let it delay when it's going to use compute into the future. So this chart is trying to illustrate, like in red, maybe it's learning how to play the game. It's going to use a lot of compute and act quite frequently, but maybe it will find moments over time that it can save compute. How is it going to do that? It's going to find moments where it can act, we can observe the world and act more sparsely. This is just a very simple method. I'm just trying to illustrate that, you know, designers have already thought about ways to save compute. Why not give the agent access to some of these tools? So what would that look like in practice? Well, whenever the agent observes, not only is it going to pick maybe left, up, right, or down, it's also going to pick a duration. After that duration, it's going to observe again and pick another action, another duration. Very simple stuff. So yeah, we've included the duration there at the top. So if you were to plot the average cost over maybe a second in the Atari game, remember 60 frames per second, maybe it looks something like this. So this would explain some of the earlier plots where there's like a exponentially decaying function like that. In my plots, I call it the decision rate, and kind of the same thing. Cool. But I've been talking about these costs, and I want to elaborate a little bit on that. And I want to give you kind of an intuitive example of what that could be. So as I was saying before, agents could get access to actions that change its use of compute in the future. But of course, the agent needs feedback. The agent needs feedback on how it has used compute in the past. In my paper, you can read about how I made this for the Atari environment, but that doesn't really matter here. I'm going to use the example of a solar panel generator. Suppose the agent is deployed onto one of these, and these tracking stations have a solar panel attached to them, and they need to track the sun. We need to give a reward signal to the agent so it can get better at this task. So an intuitive reward signal could be how much energy was exported. So this is a reward, a measure of reward that would include the amount of energy the agent is consuming as a consequence of how it's using compute. So this is an example of how you could give a reward to an agent that encompasses not only its performance on the task, so its performance, but also the feedback on how it's processing its stream of experience. And then actions could be the same as what I'm describing for the arcade environments. It could be, you know, tilting the, you know, maybe it costs energy to move the motor, but then it can wait for some amount of time. So it saves energy twice by like not orienting the tracking station and then observing in a more distant future. All right, we're going to come back to the arcade environments now. And I want to talk about how are these agents learning, because I know some RL people here would like to know that detail. First, I'll talk about how does DQN learn. So every time it observes and computes a new action, it will then observe again in the future, and this creates a transition. And this transition goes into a buffer. And then it's going to do the same thing, create a new action, observe again, and that goes into the buffer. Do it again, goes back into the buffer. This eventually, the agent is scheduled to sample from this buffer randomly, learn from these experiences, and this is how it improves. We won't be talking too much about the schedule of learning. I think that's out of the scope. And I don't change it in this paper. But I think this is useful to clarify how is my modification, how is the agent going to learn how to pick the durations better over time. And it's the same way. When the agent computes an action, it picks a duration, and this duration is now included in the buffer. So it's a similar kind of thing. It uses the same amount of compute. Cool. And we're pretty close to results. So what we did was we compared DQN and then DQN with actions that could change its compute. So they have the same amount of training compute budget, so training resources. Compute DQN can skip at 5 frames, which is the same as what DQN can do, but then compute DQN with these different actions can delay longer. It can delay not just 5 frames, but 10 frames or 20 frames or 40 frames. And this gives it very coarse control over when it will observe next and when it's how it will amortize its energy cost into the future. Cool. So let's talk about some results. So yeah, on the left here, it's a little bit different from the Pong game you saw before, because on the bottom is you're looking at what compute DQN is choosing. You're looking at when it's choosing to observe game frames, and you can maybe start to see moments where it's using more compute and less compute. And I'm going to give you guys time to maybe have a look at this and see, like, can you kind of anticipate when you think it's going to use compute? Because I'm giving you a little bit of extra knowledge. I let you see when it's going to use compute into the future. The agent is green. Oh, and compute DQN and DQN here are performing at the same human level of performance. But you're just seeing how it's using energy. Yeah. Yeah. This agent is superhuman. No. So yeah, maybe you've had enough time and you can kind of see that when the ball's maybe moving away from the agent, it's not really using as much compute. But when the ball's heading towards it, it very quickly tries to adjust the paddle at the last possible second, which is a bit stressful. And yeah, overall, the line is pretty flat at the bottom. So yeah, this is a figure in the middle to kind of illustrate how it has played this level up to 21 points. On the bottom is the decision rate in hertz. So on the far left is 1 hertz, so 1 action per second, which it can only really do at the start. And then on the far right is what DQN is locked to, so it's locked at 12 decisions per second. And walking from right to left, when it was playing this game, it reached a maximum of 8.6 decisions per second, which is using a lot of compute. And then the mean is much lower. It's 2.9. So you can see from watching the game and looking at this like distribution, it's very much leaning to the left, which means it's finding, not only is it playing at like a human level of performance, often it is playing at quite a low rate of using compute and using like its decision rate. And this is quite different to asterisks on the right here. Let's just focus on the game for a second. The compute use changes, maybe pay attention to like when waves start and when waves end. And then over time, as more objects come through the game, these objects will get faster, and the rate of observing the world and acting is going to increase proportionally. I might skip a little bit. So yeah, even between waves, I just lost a life. Even between waves, when there are a lot of objects, it's still finding small moments to save compute. And that's because it has actions that can change how it uses compute. It also has feedback. So it has some kind of signal as to maybe it's using a bit too much compute. Cool, I think we'll move on. This is a very different game, Breakout. I'm going to show you, because Breakout takes a while to ramp up in difficulty, I'm also going to show you these plots. And maybe the main plot here is this is Breakout. And Breakout's interesting because it's kind of bimodal. There's kind of a distribution here where it seems to, there are a lot of events in the game that prompt it to use a small amount of compute. And then there's another mode here where it uses much more. The thing about Breakout is that there are certain game mechanics that make the ball go faster, which makes the game more difficult. This would be the first two events are consecutive hits, so it's able to hit the ball without losing a life. And then eventually the ball speeds up when the ball hits the back rank of boxes up here, so the orange and red. And then it also speeds up when it hits the back wall, and when it hits the back wall, the paddle actually shrinks. So if the paddle shrinks, you need more precise control over the paddle so you don't, lose a life. So this kind of creates two phases where there are moments where you don't need as much precise control, and there are definitely moments where you need to be observing and changing your action rate quite quickly. And yeah, that was just a moment where the ball can get stuck behind the bricks, and sometimes the agent uses this moment to back off on the rate of observing and acting, but sometimes it doesn't.
So did you just change the reward function to also consider how many steps you wait for? Is that what happened here?
So the question was, did we change the reward function to encourage it to use less compute? Yeah, so in the paper we'll have more details, but the agent gets a small penalty every time it observes the world and chooses an action. So that incentivizes it finding moments to amortize that cost. So it will try to find moments where it can delay its next use of compute during the game. Yeah. So that can answer your question. Sorry? Yeah, so you're looking at a fully trained agent with the same number of updates that DQN would need to train on 200 million frames. So I forgot the calculation to convert that into maybe that's days or weeks of gameplay, just doing the same thing over and over again. But we'll also get into that maybe next, yes. So I think the most interesting result for me was okay, how does it actually learn? It learns over time. It learns from trying things, trial and error. So let's look at Pong on the left here. The x-axis is the rate of decision-making. The y-axis is the human normalized score. So 0 would be you're basically acting randomly. And this happens at the start of training. So at the start of training, what you're looking at here is like a scatter plot of the population of agents. So there are, I think, 10 agents here, and they're all learning. And then learning up to 40 million decisions, which is the amount of compute DQN would normally use for 200 million frames. And this like purple streak up here shows that very early on in training, it is able to quite quickly improve its performance. But there's not much of a change in terms of its rate of decision making. So Pong is kind of a game where you can master it quite quickly, master it in the sense of performance. Like you can very quickly learn how to get a perfect score. And then the rest of its training from like, the remaining duration of training, it's spending its time reducing its compute use. This is pretty different for Breakout and Asterisk though, where over the course of training, maybe in Breakout, it reduces its compute first, and then gets better, and then uses more compute to get more better. And then in Asterisk, similar kind of wiggle, and then it just focuses on performance. Yeah, I thought these were interesting dynamics of how it's learning how to play the game and change how it's using compute over time. Vlad? Sorry?
What does the color mean?
The color means on the right here. Purple is at the start of training. Bright is towards the end of training.
Maybe a follow-up to what Vlad was asking before. So I'm trying to understand in what sense this agent is more compute aware. Because so far it sounds to me like one agent has active options.
Yeah.
Have like some kind of options, and of course if you have options, you have pure data. You don't have to worry about that. This one, the other one doesn't. So can you talk a little bit more about that? And in what sense is this more compute aware?
So the question was, in what sense is compute DQN more aware of its compute cost? So it has access to actions that changes its compute cost for the next decision. And then it also gets feedback on the compute cost. And it's always constant. So it is always rewarded for, because it has a constant power draw every time it observes the world and chooses a new action, it is incentivized to repeat as long as it can, because that will decrease its overall return. Yeah, and more details in the paper for sure. There was one more hand, yeah. Yeah, the question was what determines the initial rate of decision making. These agents are randomly initialized, but they seem to start at different points in this graph. I think what happens is I'm recording the scatter plot after like 250,000 experiences, and by then it's already done some learning. So I'm not actually recording the 0th random initialization point. So this is the first few scatter plots are with like a little bit of training. So maybe that might have moved it, but yeah, it's hard to say. Yeah.
Yeah, I wanted to ask about the specific games themselves. You said that specifically like Pong would be a simpler one, so the incentive structures are a lot easier to get together. What I'm wondering is that, so just to confirm, Pong is the easiest one. Breakout is Breakout or Asterisk the harder one between the two? Because as you can see in the scatter plot, it stabilizes easier for Asterisk at some point. But isn't that the harder one? Or that might be wrong? How much?
I think Breakout is easier. So sorry, the question was which games are easier. That might be helpful to like understand its performance. And at least it's hard to say which one's easier because I can only really point to, how are these agents performing? So like it gets better performance on Breakout compared to Asterisk relative to a human score. But I'm not sure, like, maybe your question was also asking about like which ones are harder to learn, that kind of thing. Yeah, and it's kind of hard to know. Okay, and second to last result, this compute cost was like you know, in the solar panel example, maybe it's quite obvious, you know what your compute cost is, you just want net export of energy. So that's not really something that you would want to tune. But in the arcade environments, we kind of just came up with one. We came up with one that, and we have more details of that in the paper. But what I wanted to show you was when we train a bunch of agents and we change the compute cost, I wanted to see how responsive the agent was to basically maximizing its reward, accumulating more reward. And in Pong here, the y-axis is now human normalized score, and Pong is one of these games where you can't get better than a certain amount. So that's why it's kind of flat. And the color dots here are if the compute cost was very high, so then the agent would want to move as far left as possible, so lowering its decision rate. The moderate cost is what we used for the previous experiments. And then the low cost is if, you know, compute is very cheap. I didn't actually run 0, but very, very, very cheap. And it moves more to the right. Breakout, similar kind of Pareto front here, and asterisks like that as well. So anyway, the takeaway for this chart is that, hey, the agent is responsive to this compute cost. It can use its actions to, you know, meet that trade-off. The trade-off that designers probably know. All right, so let's look at overall results. These are, the y-axis is the improvement over DQN. The x is all of 40-something games. And maybe the overall takeaway of this chart here is that, you know, in a large portion of games, we're doing about the same. In a subset, we're doing a little bit better. In a subset, we're doing a little bit worse. Overall, maybe there's an improvement. But I think really what's important in this chart is to see that, you know, it's not, we didn't observe a hindrance in performance for making the agent reason about its compute. And the ordering of this chart is important because if we also show the compute cost per game, on the y-axis is this decision rate here, up high is what DQN uses, so then going lower is cheaper. What I want you to kind of take away from these two plots is that the performance and the compute savings, the compute is different per game. So the compute cost is different per game. Like Pong over here is quite low, below the mean. And then there are other games like ice hockey where it's quite high. And when I looked at ice hockey, yeah, you have to control it quite rapidly to get the puck in the goal. Excuse my lack of understanding of hockey. But I think the takeaway here is that the compute savings are kind of orthogonal to performance. Like these are kind of separate things that the agent can kind of control. The scatter plot is showing kind of a flat-ish trend. The dotted line is trying to show that trend. And yeah, it doesn't really seem to match up with performance gained or lost. Vlad?
Two questions. So for compute DQN and DQN, I guess you're in for the same number of training steps or compute steps?
Yeah, it's the same amount of training resources, yeah.
Right. And the DQN thing, this like 12 decisions per second thing, did you try changing that at all? Like, for instance, you dropped, like, if you change it to like 5 decisions per second?
Yeah.
I just wonder if it would perform more or less the same.
Yep. So the question was, did we try changing this fixed rate of using compute of DQN to like maybe see if on average it can reduce its compute cost? Yes, we did, and it has a kind of a proportionate loss in performance. And yeah, yeah, what we see is like the agent can't operate with precise control in the moments that it needs to. So that is kind of an explanation for why it drops in performance. And then in the original paper, they tried a few and picked one that had like a compromise between, you know, execution time and performance. Cool. So yeah, we're nearly finished up. I want to talk about some related work. We do know that repeating actions helps with credit assignment, and that's why I have this paper up here and the text is really tiny. Sorry about that. It's also been used in Atari before. We know it helps a lot with sample efficiency. And of course, it's been used to help exploration. Like if you pick an action and persist with that for a long enough period of time, you can explore your state space faster. Also, agents have been dynamically picking when to observe and act. In the past, it was used in the StarCraft AlphaStar agent. And then later in a workshop paper, someone showed that, hey, this could also work. Dynamically picking when to your observation delay can also work. And then there are more recent papers working on this and finding more sophisticated ways of getting this to work. These works kind of view action repeats from the perspective of improving performance. They don't really give the agent, access to its compute cost, and they're not really looking at this technique from the same angle that we are. I'm kind of approaching this from, hey, the agent could use the things that help with credit assignment and sample efficiency. This could also help with letting the agent use its compute more smartly. And like the broader vision of this paper of like, hey, maybe we should get agents to reason about how they're using compute. Like this is kind of a related topic in neuroscience where people are interested in how like your brain kind of regulates its internal function and devotes resources to thinking in certain ways and not others. Prefrontal cortex maybe has a role in that. And then the cognitive science field are also very interested in similar ideas, but they're using very different approaches. And I just wanted to give them a shout out here. And then this is like a very recent movement in RL as well. Josiah has some awesome work published at RLC at a workshop. And yeah, I'm kind of wrapping up now. I think there are kind of two untapped directions from this work that I think you guys might be excited to pursue. This work kind of shows that agents can learn when to observe and act, and we used existing methods to, of course, make that happen. And that helped it save compute. So it kind of made this graph turn into more of this graph. And I'm kind of wondering, well, we've freed up compute. Obviously, we probably want to use it. So future work could be, what are we going to use it for? I think some people would say, well, model-based planning would be really good. It could use a lot of resources. We can basically throw as much as we want at that, and we'll see an improvement. But I think immediately going in that direction is kind of missing the point of this paper. I think maybe go to model-based planning and then think, well, how could the agent decide when it wants to use its freed resources for something else? And then give it the option to devote it to planning. But maybe it can also devote it elsewhere. And then, of course, we used very simple actions that change the compute. It just delays its next observation. So maybe there could be, ways for it to construct more complex actions out of more primitive ones to change its resource consumption over time. And maybe it could efficiently learn them using the options framework in RL. And yeah, second to last slide. And then learning is stopped. A possible explanation for one of the many reasons why this happens is that designers may develop better ways for agents to use compute, and they want to update the agent with these new, more efficient ways to process its experience. But if agents could develop maybe their own ways of processing compute and they got better at a task over time, well, maybe we wouldn't want to replace them so quickly with our own designs. Maybe we could augment them with the things that we find as well. And in maybe a bigger world, the world is large and complex. And I'm not so sure designers could anticipate how the agent might need to change its use of compute over time. If agents were equipped with ways to like improve their use of resources, I'm not sure that we'd want to replace them as often. Because we expect access to compute will change over time. It may get more expensive, but it may get a lot cheaper. So I think our agents could probably adapt like designers do. Thanks for listening.